Good morning. Today in Foundations 30, we're going to take a look at section 4.4, talking permutations again, but this time when objects are identical. And how I mean by identical items, we're going to compare the words bike and book and finding how many ways can the four letters in each word be arranged and is it different? So if we take a look at the word bike, four letters, no repetition is being allowed. That's kind of implied when the letters are capital like that. We would have done this in a couple of different ways over the last few sections, as we may have looked at it as a fundamental counting principle. We would have saw our four blanks laid out. We would have decided that we had four choices, then three, then two, then one, and multiplying that out would have given us 24 possibilities. We also could have looked at it in terms of factorial. And we may have seen it as the fact that there are four letters. We're arranging all of them. 4 factorial would have given you 24 possibilities. Might have even seen it as NPR, in that we were working with 4 letters and we were arranging all 4, and you would have gotten the same 24. So there are a variety of ways that we could work with the example for the word bike. How is book different? Well, first of all, book has those identical O's. But what does that mean in terms of arrangements? So for example, clearly book, the way it's written, is one possibility. As is, if I were to switch the last K and the last O, that would be a different arrangement. But what if I just interchanged the O's? Would that be considered a different arrangement? And no, it is not. And so therefore, if I were to look at interchanging the O's in the word book, that would not be a different arrangement. It has to have a different appearance. So every time that we are eliminating where those two O's switch and it doesn't look different, we're eliminating some of the possible arrangements. So how do we go about doing that so that we can find all the possible arrangements? Well, this is the approach we're going to take with identical items. If we're arranging identical items where we have n items, but A are identical, B are identical, C are identical, we're going to start with taking all of the items we have. So in this particular case, we would have 4 letters in the word book. But because we have identical items, the 2 O's, we would divide by 2 factorial. And so if you were to take your 24 and divide it by 2, because this is what it works out to be, we would have 2 possibilities. So again, we have 4 letters in the word book, but we have 2 O's, and we have to divide out where those 2 O's change spots but do not actually have a different appearance. So this is a formula we're going to take a look at when we have identical items. So the problem with these types of situations is making sure that we can identify when we have identical items. So let's take a look at this situation. Mountainous regions of India, China, Nepal, and Bhutan. We see prayer flags. Each flag has a prayer written on it. Color is used to symbolize different elements. Green for water, yellow is earth, white is for the air or the wind, blue is sky, space, and red is fire. So it says how many different arrangements of the same prayer. So that is implying some identical words on it. If they have 9 flags where 1 is green, 1 is yellow, 2 are white, 3 are blue, and 2 are red. So as soon as we get to these identical items, the same prayer flags on the 2 white, they would be identical whether you would look at the 2 whites, the 3 blues, and the 2 reds. So the identical items formula says we're arranging 9 flags in all. I can count them and that adds up to 9. But we have 2 blue flags that we are going to account for. We have 3 blue and then 2 red. Now it is important with these questions that we punch them into the calculator correctly. Sometimes what I find to be efficient is that we calculate the top and the bottom separately. So if you go on your calculator and do 9 factorial, we get 362,880. 2 factorial works out to be 2. 3 factorial is 6. And another 2 factorial. So we end up with 362,880 divided by 24. And when we do that calculation, we end up with 15,120. So just in terms of using the calculator, is there a way that we can avoid having to do each of these individual steps? Can we put it all into the calculator? Well, yes, we can, but we need to remember order of operations, that the bottom is all being calculated together as a total before it is being divided into the top. So on your calculator, you may need to do something like this. You may need to put in your 9, and remember where we found our factorial under math, back up to probability. Number 4 was factorial. Whoops. Not number 1. Let me go back and delete that and try that again. That was under math, back up to probability, number 4, factorial. Now, I want to divide by all of those values. And so it does help to understand what factorial means, because going to and then math and then back to probability and finding factorial and multiplying that to 3 and then math. It's a lot of buttons to press. So with some of these questions, it sometimes is helpful if we know that 2 factorial is just 2. And that's what I'm going to do with the last one. I'm not going to put 2 factorial. I know it's equal to 2, but close the bracket. So all of those numbers are calculated together to give us our 15,120. So we had identical items. We had to account for the items that were identical, but when they moved, for example, the 2 white changed spots, it wouldn't appear to be different. So the next example I have for you is connected to these prayer flags, and it says, suppose that you have those 9 flags, but this time 3 are white, 3 are red, and 3 are green. They want to know if there would be more or fewer than the 1,520 arrangements that we had here. And if we were to do this question where we had 9 flags in all, but again, those identical, 3 factorial, 3 factorial, 3 factorial for each of our colors that were repeated, and predicting, would we have more or less than the previous 15,120? Well, we're dividing by more numbers, so I would think that we would end up having less. And in the end, if you take the 362,800 we get from 9 factorial, and 3 factorial is 6 times 6 times 6, which works out to be 216. We end up with 1,016 or 680 different arrangements, definitely less than the 15,120. So the identical items is a fairly straightforward formula. A repetition is assumed to not be allowed, being that that these 3 flags will be placed 3 times somewhere in our lineup, but we couldn't have a 4th or a 5th or a 6th white one. And that goes hand in hand with factorial, which is implying that repetition is not allowed. So let's have another look here. This time we're talking about the letters of the word Canada. Again, capital letters means one of each of those. If the first letter must be N and the last letter must be a C. So right away when I start reading this last bit here, to me these are special conditions. And so as soon as I see those special conditions, that makes me think about the fundamental counting principle. So to do this question, I'm going to take and draw out 6 blanks for the 6 letters of the word Canada, 4, 5, and 6. I'm just going to make note of my specific conditions here, that the first letter has to be an N and the last letter must be a C. So if I'm going to fill in what options I have, there is only one letter in Canada that's an N. So that means I only have one choice of a letter to go in this spot. There is only one C in the word Canada, so I only have one choice there. Now these 4 spots to fill them. Normally what we would have done with the fundamental counting principle is we would have went 4, 3, 2, 1. But when you take a look at the remaining letters, we have 3 A's. And so therefore, when I flip those A's around, they're not going to appear differently. So in these middle spots, what I tend to do is I think of it as 4 factorial, but in the bottom, I divide out where the 3 identical A's are going to change spots, but not appear differently. So in the end, if we were to calculate 4 factorial divided by 3 factorial times our 1s, we would only have 4 different ways that we could arrange the letters of Canada that meet these conditions. So when we have special conditions, yes, we still have to think about fundamental counting principle, but arranging whatever's not part of the special conditions, we have to look at possible identical letters. So how does that change here? Again, I've got another Canada situation. How many different arrangements are there for the 6 letters of the word Canada? First of all, if there are no conditions, for part A, we can put whatever we want. We have the 6 letters of Canada, but once again, we have the 1, 2, 3 A's that when they switch spots are not going to look different. And so 6 factorial divided by 3 factorial works out to be 120. What if we want the first letter? Now I changed it. I didn't want C because I wanted us to see where or how things are going to be different if one of those identical letters is part of the special conditions. If the first letter has to be an A. So again, I have a special condition in place. So I need to start with my fundamental counting principle. And the first letter has to be an A. There's no other special conditions for the remaining 5 spots. So when I go to figure out how many possibilities I have here, we have to think of it a little bit differently in terms of how many different appearances is this first letter going to have. And yes, there are 3 A's, but there is only one possible appearance that we can possibly have here. Now, if you don't like that, what you can think of in place of that A is this, is that there are 3 A's. So I could think about those 3 A's, but there are 3 of them that are identical. And so it's a little bit less, appropriate, I guess. I'm not too sure if that's the right word, but that would still work out to be there's only one appearance that we could have in that first spot. Now, what about the 5 remaining places that we have to fill? There's no special conditions here. We have 5 letters left to choose from when A is used up. But the fact that we had 3 A's, but we already used 1, that there is only 2 A's left. And they are still identical, so we would divide by 2 factorial. And we would end up with 1A stationary here. That's not going to move. But the other 2, when they rearrange in these remaining spots, will not look different. And therefore, we have to account for the possibilities of where they are changing, but not a different appearance. So if we do 5 factorial and we divide by 2 factorial, we are left with 60 possibilities. All right. So when we talk about special conditions, we still have to think about our fundamental counting principle, but the identical items approach is definitely something that we have to consider as part of these questions. All right, I have one more that we're going to take a look at, and it seems a little bit different than the previous one, so let's just take a look at it. Julie's home is 3 blocks north and 5 blocks west of school. It says, how many routes can Julie take from home to school if she only travels either south or east? So this is her house and she's going to go to school. When she does walk to school, she's going to walk directly there. She's never going to backtrack and go a different route around the blocks. It's a direct route as possible. So only ever going south or east. So this question is a little bit different. I'm going to show you two ways to approach this question. We're going to pretend for a moment that Julie's school is right here. If Julie can only go south or east, she has only one route to get to this corner, if that's where school is. Well, pretend for a moment that, let's say, school is here instead. And if she's going to walk directly there, no backtracking, there's only one route to get there. What if school was here? How many routes would she have to get from home to school again if she only ever goes south and east? Well, this would be one possible route. This would be a second possible route. And so she would end up having two possible ways to get to school if it was in this corner. All right, well, I'm going to continue this. What if school was here and she had to go from home to school? Well, there would be only one route that she could take. She could only go straight down, and therefore she would have one way to get there. What if school was over here? She would only have one possible route to get to school there. But what if school was here? How many routes would she have to get to school if school was in this corner? Well, we could go straight east and then straight south. That would be one. We could go straight south and then east. That would be two. Or she could go south and then go east and then back south again. So there's actually three routes to get here. Same thing if school was over here. We would have one route, two routes, or three routes to get to here. Now I'm doing this slowly because I'm wanting you to see that there's a bit of a pattern as to how these numbers come to be so that we can not have to draw out every possible route because it gets very complicated the farther we move ahead. What you may notice is that there's a connection between these two numbers to get to this number. There's a connection between these two numbers to get this number. There's a connection between these two to get to this number. So that pattern is going to hold true if I were to talk about how we can get to this corner here, and that there are going to be 6 possible routes that we add to get to this corner. We just need to make sure that we go back and fill in that on the straightaways. Straight south, there's only one route. Straight east, if we're going to school here, there's only one route. Or straight east to here, or straight east if school was here, one route. But after that, we can start to fill in the numbers using that pattern that these two numbers are going to add to get me this corner. These two numbers are going to add to get me to this corner, and so on. Adding these two to get me here. Adding these two is going to get me 10 routes to this corner. This corner is going to give me 20. Backing up and filling in some of these other ones to get to this corner, adding these two together is going to give me 5. Adding these two together to give me this one will be 6. This one will be 15. Adding these two corners to get here is going to be 21. 15 and the 20 corners are going to add up to 35. And then finally, the 35 and 21 corners are going to add up to 56. So we would be able to say that there are 56 routes for Julie to go from home to school. Now, that is an appropriate method, and that works, and some people really like that method. But how does that fit in with our identical items? Well, in total, no matter which way Julie walked, she had to go 8 blocks. And out of those 8 blocks, she definitely anywhere along the way had to go south 3 times. So somewhere she went south, south, and south. Like, for example, if she went straight south, and then she would have 5 blocks that she went east. Well, if we were to arrange rearrange these 8 letters in such a way that it's going to be different, not just going and changing these 2 S's, because that's not going to be different. Well, we end up having our 8 blocks, 8 letters really that we're arranging, of which there are 3 identical south directions, 5 identical east directions, and if you were to take out your calculator and do the 8 under the math, finding our factorial, and then dividing by both of those numbers in the bottom, the 3 under the math, backing up to probability, number 4 is factorial, and multiplying that by 5 factorial. Let me get my factorial again here. Number 4, closing the bracket for the denominator, hitting enter, we're going to get that same 56. So today, when we talk about permutation problems, we have to pay attention to if there are identical items. We're going to have to make sure that we are accounting for them in the denominator, and watch out for those special conditions where we have to start with some fundamental counting principle. But that's all for section 4.4. Have a good day.